It just doesn't. It has a gigabyte. It's a gigabyte. It's bigger.
So we've done this method, we've done washer method, and so today we're doing volume by different cross sections. So so far, all of our cross sections have been circles. Cross section just means if you were to take your solid, if you were to cut it, if you were to slice it and open it up, what shapes will you see? And because of the rotation, it's always going to be circle related. Because it's circle related, we always have these circle cross sections. But now we're dealing with cross sections that are different shapes, such as we're going to create volume by cross sections that have shapes of, could be rectangle, could be square, could be triangle, could be semicircle. But we're going to find the information the same way as before. We're going to still do either top minus bottom or right minus left. We're still going to find the balance the same way. We're just going to take our segments. Before we called it radius, but now we're going to call it the base, and we're going to insert into the appropriate formula. So after you get your information, then plugging into the formula is easy if you know what formula to plug into. Right. So the hardest part is still going to be building your quote unquote radius and finding your value. And then if it's top minus bottom, everything's in terms of x. If it's right minus left, everything's in terms of y. So all the hard things are still going to carry over from before. So that's all the same. And we're just going to have to plug it into a different formula. But once you understand that, then you're going to feel like it's not much different than before. Okay, one second. So let's go to page 17. And just to let you know that these shapes are going to be very strange looking. We don't have to worry about what the shape of these objects look like. We just have to be able to know how to put it into the formula. Okay, but I will give you some demonstrations as to what these graphs can look like. Okay, so cross section, again, is a shape that results if we cut the object in half and look at the resulting shape sideways. So this method, washer method, we know washer has a hole in it, but still it's circle related, right? If you open it up, washer just has a hole in the middle. It's a circle within a circle, but it's still circle related. And the reason that we're getting circles is because we're doing a 360 rotation, right? That 360 rotation is what causes the circle. So we've basically been doing this formula before. It's just that our area has always been circle. So it's been like pi r squared minus pi little r squared, but it's always been circle related. But what's different today is that we're just going to be inserting something different into this region. Okay, we're going to find whatever area we're dealing with and insert into that integral formula. Okay, so the volume problem we've covered so far involves taking the shaded region and rotating about a center and axis of revolution. So our area has always been either pi r squared or pi r squared minus pi little r squared. So now we're still going to have a shaded region, but instead of taking this shaded region and rotating it, now we're going to let it act as the base of the three-dimensional object. Okay, we will now build the cross-section area on top of the space. There's no longer a rotation because there's no longer rotation. There's no longer going to be a pi. There's no longer going to be a pi r squared. All right, so let's say we have the shaded region here. This is kind of like a quarter circle. The shape of the shaded region has no bearing. It doesn't mean anything. But let's say we wanted to build different sized squares on top of this base. Okay. Then your object will look something strange like this. So imagine this length. Let's say this is a length of 1, then that means we want to build a square of height 1. Okay. If this distance is 2, then we want to build a square that's coming out of the page of height 2. And if this is a distance of 5, then we want to build a square that's coming out of the page. So if you can imagine, these infinitely thin squares are all kind of stacked together. And because of that, they're creating these kind of odd shaped objects. Okay, again, we never have to worry about what the shape looks like. We just have to be able to gather the information to build whatever volume that we're trying to build. But if you can imagine taking this and slicing it in half and opening it up, you're going to see squares. Okay, and that's really the whole thing here. If we're building triangles, then we're going to have an odd shaped object, but if you open it up, you're going to see triangles as cross sections. Okay. So before, for area, we built heights of rectangles, and then for disk and washer method, we were building radius. And now I'm going to call these bases. Okay, and the base is just going to represent a component of these different shapes that we're building. So we can be building a square. We can be building an isosceles right triangle. We can be building an isosceles right triangle with a hypotenuse on the base, a rectangle, an equilateral triangle, semicircle. But notice, if I can find a base length for whatever orientation I'm putting in, I can just put it into whatever respective formula and then put an integral next to it. So, the hardest thing is getting the base and getting the bounds, just like how we did with this method and with area. But now we're just, instead of inserting into an area, into a circle formula, we're inserting into the appropriate shape formula. And then we are going to be responsible for all these formulas. Okay. All right, so example 1, find the volume of the solid of the base bounded by the curve square root of 1 minus x squared, y equals 0 and x equals 0 in the first quadrant. So basically, it's this shape. And we're going to be finding the volume of this object. Okay. But this is kind of drawn in a 3-dimensional way. We're going to draw it in a 2-dimensional way like we normally would. And but we're not going to have to draw the shape. We just have to build the base length. Okay, so here's square root of 1 minus x squared. It's just like a quarter circle in the first quadrant. So this is the square root of 1 minus x squared. You got y equals 0. That's the x-axis. You got x equals 0. That's the y-axis in the first quadrant. So here's our shaded region. Okay, so this is the hardest part, I believe, in this section. It's just drawing your base in the correct orientation. Okay. I know it doesn't seem like a big deal here, but this is where a lot of students have trouble. Okay. Parallel to the y-axis. Which direction is that? Vertical. Okay, vertical. So all you're going to do is you're just going to connect from one end to the other. A vertical base. So pretend like this is area or this method. You're just going to do top minus bottom. You're going to find the bounds the same way, and that's the hardest part. Okay. But you may be looking at this going, that doesn't seem so hard, right? Parallel to the y-axis. What's so hard about that? Well, there's 4 different variations, and it's easy to get mixed up if we don't read it carefully, right? So you can have parallel to the x-axis. You can have parallel to the y-axis. You can have perpendicular to the x-axis, you can have perpendicular to the y-axis. Right, and if we're just assuming that we're reading parallel instead of perpendicular, that can throw us off, right? If we're thrown off, then that just leads us down the wrong path. So just be careful. There's 4 variations. You just have to make sure you're reading the problem and just carefully making sure that you're in the correct orientation. Okay. Right, so in this case, it's vertical because parallel to the y-axis. What's another way of saying vertical? Perpendicular to the x-axis, right? So, right, if we're not careful, it's easy to get thrown off if we're thinking parallel is perpendicular or thinking the y is the x-axis. Okay. All right, so pretend like this was this method or area. You're just going to do top minus bottom. The top of my base length is touching the curve. The bottom of the base length is touching the x-axis. So I'm going to build my base. Base equals. So instead of calling this height or radius, now I'm going to call it base because I'm going to adapt it to whatever shape I want to build on top of this base. So top minus bottom, the top is sitting on what? Yeah, the square root of 1 minus x squared. Minus, and the bottom is sitting on the y equals 0, right? Okay. Okay, let me just show these formulas that we're using here. All right, we do need to find the bounds. This is top minus bottom, so we know we're going to do x1 and x2. That means I need to find the left and right bounds. The left one is easy. What's the left x value? 0. And the right one here, I could just set the square root equal to 0 and solve for x, right? Square both sides. So x equals plus or minus square root of 1, but we're only looking at the first quadrant, so it's just going to be 1. All right, we have our bounds. We have our base. We just have to pick out which shape we want to build. What shape are we building? Cross sections are what? Squares, yeah. So whatever shape we're building, we're going to put it into that area formula. Is base squared. So I'm going to take my base, which is square root of 1 minus x squared. I'm just going to square it. Now, once I have my area and my bounds, now I can put it into my volume formula. Before it was pi r squared, putting and then inserting and then putting integral and dx on either side. Now we're taking our area, whatever it is, and then now we found the area of one of the squares, and now we're going to accumulate that over the entire interval so that we can add up all these infinitely thin areas of squares. Okay. Why do we not have pi here? Because it's not a what? It's not a circle, right? So I know we're going to get used to seeing pi a lot because we did it for disk and washer method. We always had pi in front, but volume of cross section, the only time you have pi is the semicircles. That's the only time that is circle related. Everything else, there's no pi. Now I can put this down or I can clean this up. This is what I can clean this up to be just what? Just 1 minus x squared, right? I don't have to write the whole square root. It just cleans up. I mean, you can put it that way, but this makes it a little easier to not have to write all that. Okay, the rest goes in your calculator. Again, you gotta just remind yourself, don't attach pi because this is not we're not rotating here. This is not a circle, but it's still a volume, so still units cubed. Next page. Example 2, find the volume of the solid at the base is bounded by the curve y equals x squared and y equals 4. So let's go ahead and graph these two. You got a parabola and you have the horizontal line. So we're trying to get to our shaded region first. Y equals 4. Okay, so make sure you know what shaded region you're working with. There's no axis of revolution. We're not rotating anything. Imagine this is the flat surface, and you're building these different shapes on top of the flat surface. All right, so the next thing we need to do is we need to make sure that we know which orientation we're working with, right? So this is going to be a horizontal base. This is going to be a vertical base. Okay, so be careful here. Parallel to the x-axis. Which direction is that? Horizontal, right? X-axis is here. Parallel to it, so horizontal. This is a horizontal base length. So guess what we have to do here? This is right minus left, which means we have to do what with our equation? Got to rewrite it, right? So anytime you see right minus left, whether it's area or this method or Washer method or cross section, you know that you have to spend time rewriting your equation. Okay, so the y equals x squared does refer to the parabola, but it's not in the correct form. So if I want to solve for x, what's x equal to? Plus or minus square root of y. So in the calculator, we're going to use x, but on paper, we need to be able to solve for x equals because it's not the same equation. So yeah, so if I did y equals x squared, that's not the same thing as x equals square root of y. Now in the calculator, you're going to do square root of x, but that's not the same thing as just calling the x squared because we're creating a different equation. I know the calculator, it feels strange because the calculator can't handle y, so we have to use x's after we get our things set on paper. Now, in this case, are we going to use both these equations? Yes. Okay, and the reason why is because you have two branches, and the two branches make up the positive square root of y and the negative square root of y. So I'm going to highlight them in different colors here. So this positive side is the x equals square root of y. And this negative side here in green is the x equals negative square root of y. Okay, now we have this in the correct form. Now we can build our base length. Before we called it radius, now we're calling it base because it's going to be a component for one of the shapes that we're going to build. Okay, so right minus left. What's the right endpoint of my base length touching? Root y. Okay. Minus, what's the left endpoint of my base length touching? Negative root y. What's going to happen here? Yeah, so it's not going to cancel out, right? The negatives cancel out, but we're just going to end up with a positive what? Plus root y plus root y. Not 0. 2 root y. Yeah, you got 1 root y plus 1 root y. That gives you 2 root y. If it was root y times root y, then that'll become y. But 1 root y plus 1 root y is 2. Okay. Are the bounds easy to spot in this case? Okay, we want to find the lowest and highest y value. What's the lowest y value? 0. What's the highest y value? 4. So sometimes your shaded region is easy for you to find the bounds. Sometimes you have to set equations equal, especially if it's not clear. Right? But in this case, we have the lowest and highest y values easy to spot. Okay, now we got to build the area. Okay, so what shape are we building here? Well, okay, so here's the thing. The base can take on different shapes, but we're never going to look at the shape of the base. We're always going to look at what they're describing. So the cross section here, isosceles right triangle with hypotenuse on the base. So this is a very specific way of building the triangle. The right angle is actually going to be sticking out of the page. So I adapted the formula so we can kind of just use it rather than have to derive it every time. Isosceles right triangle with hypotenuse on the base, just 1/4 base squared. We have the base, we have the bounds. Let me build the area first. Now, if you want to jump directly to the volume formula, you're welcome to. I just want to kind of make sure that we're understanding where each of the steps are coming from. So I'm just replacing base with 2 root y and inserting into my formula. And once I have my area, now I can just put integral and dx on both sides with the bounds, and that will turn it into a volume formula. Okay, I'm just cleaning up as I go because these are relatively easy to work with. But if I want to, if you want to put everything in the calculator at once, you can. But here, I think I can just, yes. Yes, yeah. So if I have a number here, I'm going to see if I need to enter it in the calculator. In this case, yeah. So if I ever see pi, I want to always leave it out of the calculator. But if it's a coefficient, you can either decide to put it in the calculator or leave it out and yeah, multiply it through or make the calculator do it. So I would say it's up to you. But with pi, definitely don't put in the calculator because then it's not going to get you as clean of an answer. Okay, so I just cleaned it all the way down to just y dy. Okay. Make this so I can do this by hand or put it in the calculator. But if I did y squared over 2 from 1 to 0, I'll get 16 over 2 minus 0, which is 8. But you can use your calculator on the test, so you can just enter this in. Yes. Oh, sorry, my bad. It should be 0 to 4, my bad. Yeah, lowest y value to highest y value, 0 to 4. Okay, can you guys try example 3? Example 3 is going to be the same shaded region. Okay, and see how far you can get. All right, so I think yeah, because it's still y equals x squared and still y equals 4. Yeah. But look at the description for the orientation of the base and look at the area that we're building on top of the base. So again, never look at the shape of the base. It could be anything. It's not going to, the shape of the base has no bearing on what we're trying to do, right? You're always going to be given very specific direction as to what shape you're building on top of the base. All right, perpendicular to the y-axis. Which direction is this? Still horizontal, right? See how different ways of representing horizontal, but if we're assuming that, we're always associating perpendicular with up or down or parallel with left and right, we're going to get thrown off, right? So just pay attention to the combination of these words and let that guide which direction you're building, right? So y-axis is vertical, but perpendicular is going to make it horizontal. So can we carry a lot of information from above? Yeah, same, right? Same equations, same base, same bounds. Just a different cross section. Okay, my formula is power over 8, base squared. My bounds is still going to remain from 0 to 4. So you can do whatever you like. You can leave that power over 8 in front and just do the integral, or you can involve the 4 and 8 to reduce. Plug that in the calculator, but my suggestion is just at least make the pi, leave that out of the calculator, whatever you want to do. Okay. Any questions? All right, example 4, let the region R be the area enclosed by the function y equals natural log of x. That's the curve. 1/2 x minus 1, that's the linear. If the region R is the base of the solid such that each cross section perpendicular to the x-axis is an isosceles right triangle with a leg in region R. Find the volume of the solid. So we have to decide which direction to build our base. Is it top minus bottom? Is it right minus left? We also have to make sure that after we build our base, that we're putting it into the correct formula. And then something else here, what do we need a calculator for here? The bounds, right? The bounds is not, if we try to set these equal to each other, it's hard to solve for x. So practice using your calculator, do your intersections, find those intersections. Now, if you're using a 36 Pro, what you may have to do is this. You may have to, after you set them equal to each other, you may need to edit function and set everything equal to 0, put this into the calculator, and then do a table of values and see when your x value changes from negative to positive or from negative or from positive to negative, and those are your bounds. So it's very, it's more tedious on the 36 Pro because you don't have a graph, you only have table to work with. But if you don't have a graphing calculator and you're wanting to use 36 Pro, I can walk you through those steps to find your bounds. Okay, so which direction is this? Perpendicular to the x-axis. Vertical, yeah. So vertical, that makes it easy, right? Because we don't have to change our equations. Our equations are good to go. Right, now when you do top minus bottom, what do you have to be careful about? Is that correct? Parentheses. Okay. I'll keep reminding you of that because, you know, if you leave out parentheses, it throws off your entire answer. Yeah. Yeah, question. Axis of revolution. Because we're not rotating around an axis, right? Because we're building these right triangles on top of this base. So this is trying to show what this graph looks like. Imagine these triangles sticking out of that shaded region, and it's creating these odd. I can't draw them, and we don't expect to draw them either. It's just have to be able to get the information and put into the formula. Okay, so intersection, you're going to graph both of them. You're going to use second trace intersect. You're going to pick points around the around your first intersection, and then it should be able to get those x values. Okay, once you build your base, isosceles right triangle with a leg on the base, we're going to use this 1/2 base squared, and then our volume with the bounds in place. Y equals. I always do. It Zoom 6. It always gets me in that. Zoom 6 always gets me to my standard window, and then from there I can do a box. So now do Zoom box and draw a box around that region. Yeah, make sure you're practicing getting those intersections, that you can read those intersections off your calculator. Yeah, so, yeah, did enter it. Oh, you did already, so it's drag. Oh, do Zoom. What? Yeah. There, I mean, just give yourself a little bit. There we go, yeah. Very good, yeah. Thanks. Okay, so hopefully you guys find a lot of similarities between this and this method. The only thing you gotta be careful about is, that's different, is that make sure parallel, perpendicular to the X and Y axis, that you're paying attention, that you're spending time making sure that you're drawing it correctly. And then the formulas, we have to be able to know how to, yeah, we have to be able to memorize those as well. So those are also required on the exam. Any questions? Okay, so with the time that we have, I'd like for us to do a washer method FRQ. So the handout that you picked up, it's meant to be non-calculator, so I want you to try working through it without a calculator. I'll go through the key with you. The key's on the back, but I want you guys to try it first, see if you can do all the orientations and the rewriting of equations and finding the bounds and let me know if you have any questions about your calculator, especially. Yeah, for this problem, it's meant to be non-calculator, but just for, yeah, practice purposes.
So anything about
No, the test is going to be calculator, but right now I want to practice without it, because there's a use substitution involved, but just. But on the test, you will get to use your calculator. Yeah, I'll go over it. Well, 5 minutes. Find your order pair, find your slope. And find that, yeah, so to find m, you gotta find the derivative, plug in. And then use. Yeah, plug one half into the derivative. And find. But then, okay, so finish that equation. I plugged in the 1/2, but they already gave me the order pair, so I'm gonna just rely on that. But if I didn't have the 1, I can find that 1 just given 1/2. Slope comes from the derivative, so f of x, you can find s prime going to the power rule. And then plug 1/2 into the derivative to get your slope, and then point slope 1. Part B, find the area of R. So look at your shaded region. Easier to do top minus bottom, or is it easier to do right minus left? Top minus bottom in this case. Because our equations is already in terms of x. So, I mean, if we want to do right minus left, you can, but you got to rewrite your equation. And it's already y equals, so it's already perfectly set up for top minus bottom. Yeah.
You know,
This one, you always want to explore top minus bottom first. But if it feels like it's too complicated, then maybe right minus left. But this case, it looks like I can draw, vertical, rectangles and I'm getting consistency all the way through, so top minus bottom. And typically we prefer top minus bottom unless we're forced into right minus left, like if you're rotating around the vertical axis. Or if if it tells you that your, cross section is horizontal, then you're forced into right minus left. You could, but I think that's harder. Okay, so for part B, top minus bottom. Draw a rectangle, represented rectangle. And then build the bottom and top of that rectangle. The top is sitting on the sign. Yeah, well, we kind of have an idea what x cubed looks like. So x cubed kind of has this shape to it. So we know that x cubed is kind of concave up. So that kind of helps us know that. This is not just integral of sine x, integral of sine pi x. So we know that pi x is going to produce something. It's really just produces a 1 over pi in front because of u substitution. Think of it as chain rule, but going the other direction of chain rule. So instead of times pi, it's going to be times 1 over pi. Okay, so if our u value is pi x, find the derivative. Pi x derivative is pi, solve for dx, dx goes to u over pi. We make our substitutions, pull the 1 over pi out, and we know the integral of sine is negative cosine. Bring back the pi x, and now that we found the antiderivative, we don't do plus c here because we're dealing with bounds. Now we can do a half bracket. We can involve the upper and lower bound. So 1/2 gets inserted into the expression first, minus big parentheses, followed by the 0. The test is going to be calculators. We go into the calculator, but I don't want us to forget how to do these problems by hand. So that's going to be something that is going to show up on the AP exam. Okay, part C and D is where we're either doing wash or disk method because now we're rotating that shaded region around an axis. So either horizontal axis or vertical axis. But we'll pick up C and D tomorrow. At the beginning of our test review, we can go into our test review. You guys do have homework for this cross section, just a couple problems from the textbook. I'll check that homework tomorrow. Go get your phones.
Is your mom just out as a mouse?